Imagine you're holding a tiny magnet in one hand and a piece of copper wire in the other. Nothing fancy, just two ordinary objects, but hidden inside both of them, inside everything you can touch, taste, bump into, or complain about on a Monday morning, are electrons. Zillions of them. More electrons in your body alone than there are grains of sand on all the beaches you've ever gotten stuck in. Now here's the strange part. Every single electron, no matter where it is in the universe, is exactly identical to every other one. Not pretty similar. Not close enough for government work. I mean identical in the most absurdly strict sense you can imagine. Same mass down to more decimal places than you'd care to write. Same electric charge, same magnetic behavior, same everything. You can't paint one red and another blue. You can't scratch your initials into one. If the universe were a gigantic warehouse full of electrons, there would be no serial numbers, no labels, no way to tell if you swapped two of them when nobody was looking. And that's already weird, right? Because everything else in your experience is distinguishable. Even identical twins have little differences. Snowflakes, fingerprints, voices, opinions about pineapple on pizza. Differences everywhere. Nature seems to love variety, except with electrons. Nature went full copy-paste. Now suppose I told you there's a way to take this idea one step further. Not just that all electrons are identical, but that there's actually only one electron. One, not one kind. One single electron zigzagging through all of space and time, playing every role in the cosmic drama. The electron in your eye that lets you see this screen. Same one that helped light a star billions of years ago. Same one that might be in a distant galaxy right now, minding its own business in a chunk of rock nobody has named. If that sounds like I've had too much coffee, good. That's the right reaction. Because the fun starts exactly where your intuition throws up its hands and says, that's ridiculous. Let's poke at that feeling. You're used to thinking of particles like tiny marbles. Lots of them. They move around, bump into things, bounce off each other. If I have 3 marbles in my pocket and you have 2, we can pour them on a table and count 5. Simple. Each marble has its own little story. But quantum mechanics, that strange rulebook nature uses at very small scales, keeps whispering something different. It says be careful. These marbles don't come with name tags. When 2 electrons meet and scatter off each other, there isn't a fact of the matter about which one is which afterward. Asking which outgoing electron used to be this incoming one is like asking which corner of a perfect circle is the original one. The question assumes a distinction that just isn't there. Physicists noticed this early on and shrugged in a very scientific way, which is to say they said, that's odd, and then wrote down some equations. The math worked beautifully if you treated electrons as fundamentally indistinguishable. Not just practically indistinguishable, like 2 screws from the same factory, but ontologically indistinguishable. There is no underlying thisness to keep track of. So here's the leap. If you can't ever tell electrons apart, if the laws of physics never need to label them, if every experiment treats them as perfectly identical, then what exactly forces us to believe there are many of them? Counting, you say. We measure electric charge, we see currents, we build detectors that click when electrons pass by, sure. But those measurements only ever tell us how many interactions are happening, not which electron is doing what. It's like watching footprints appear in the snow. You can count how many times something stepped there, but if the same person ran back and forth 100 times, you might mistake it for a crowd. Now let's stir time into the mix, because time is where things start to get deliciously strange. In everyday life, time feels like a one-way street. Eggs fall and splatter. They don't leap off the floor and reassemble themselves into omelets. You remember yesterday, not tomorrow. But when you write down the basic equations that describe electrons, especially when you make them compatible with relativity, the physics of space and time, they don't strictly forbid motion backward in time. The math is oddly symmetric. A particle moving backward in time can look an awful lot like a different particle moving forward. In fact, there's a neat trick in the equations. What we call a positron, the antimatter partner of the electron with opposite charge, can be described mathematically as an electron moving backward through time. Now pause. Let that sink in. We already know electrons and positrons can pop in and out of existence in pairs. In high-energy processes, you get an electron here, a positron there, they zoom around, and eventually they might collide and annihilate into light. From one viewpoint, that's 2 particles being created and destroyed. From another viewpoint, the math doesn't complain about this. It could be a single electron that, at some point, turns around in time and comes back the other way. So instead of many electrons being born and dying, You could imagine one electron tracing an incredibly tangled path through spacetime. Sometimes it's moving forward in time, we call that an electron. Sometimes it's moving backward, we call that a positron. When it switches direction, it looks like creation or annihilation to us, because we're stuck experiencing time in one direction. It's like watching a long, loopy piece of string pass through a flat sheet of paper. If you're a two-dimensional creature living on that sheet, you'd see little dots appear where the string pokes through. A dot appears, a particle is born, moves around a bit, then disappears. A particle is destroyed, but from the three-dimensional viewpoint, it's just one continuous string weaving in and out. Now trade string for electron world line and sheet of paper for or experience of time, and you've got the picture. Suddenly the outrageous claim there is only one electron doesn't sound like mystical poetry. It sounds like a mischievous but mathematically legal interpretation of the rules we already use. Of course, nature doesn't hand out prizes for clever interpretations. The question is always, does it match what we see? And here's where the idea becomes both fascinating and frustrating. In many ways, it doesn't matter whether you say there are countless identical electrons or one electron taking the scenic route through time. The observable predictions can come out the same. Physics, at its core, is about what you can measure, and both pictures can be arranged to agree with experiments, at least at a certain level. But the mental image you carry changes how you feel about the universe. One picture says reality is made of an enormous crowd of identical actors. The other says there's a single actor, changing costumes and darting on and off stage so fast that we mistake it for a cast of trillions. And if that doesn't make you lean back in your chair and grin a little, you might not be paying attention, because now we're not just counting particles. We're questioning what many and on even mean when time itself is part of the playground. And once you start tugging on that thread, the whole sweater of reality begins to loosen in the most delightful way. Want me to keep following that electron on its wild trip? All right, so let's keep our eye on this hypothetical little rascal, our one electron that's apparently too busy to sit still and be just one thing at one time. Picture spacetime not as a rigid grid, but as a big, flexible stage where events happen. Not just where things are, but when they are. Every particle traces out a path through this stage. Physicists call that path a world line, which sounds fancy but really just means the story of where something is at each moment. For a baseball, that world line is pretty boring. It goes forward in time, arcs through the air, hits the ground, rolls under a car, and that's the end of its athletic career. Smooth, continuous, always moving forward in time. But for an electron, if we take the equation seriously, that world line doesn't have to be so well behaved. It can wiggle, it can loop, and mathematically speaking, it can even double back in time. Now, you might say, hold on, going backward in time, that's science fiction stuff. And sure, in your daily life, you don't see your coffee unspill itself. But down at the level where quantum mechanics and relativity shake hands, the rules are written in a language that doesn't strongly prefer forward over backward. The basic equations are surprisingly tolerant. They don't jump up and shout, "Illegal move," when time runs the other way. Here's a way to get a feel for it without any equations. Imagine you're watching traffic from a helicopter at night. You see headlights moving along the roads. Now suppose some strange effect in the atmosphere sometimes makes a car look like it's moving backward along its path, even though it's actually just turning around in a looped overpass system. From your limited viewpoint, you might say, "Ah, a car going the wrong way!" But from a higher perspective, it's just one continuous route with a complicated shape. In quantum field theory, the framework we use to describe particles like electrons, we often draw little diagrams to keep track of interactions. Lines come in, lines go out, they meet at points. An electron comes along, interacts, maybe a photon is emitted, maybe a pair of particles shows up, and so on. These diagrams are bookkeeping devices, but they also hint at a deeper picture. Sometimes, in these diagrams, a line representing an electron bends around and heads backward in time. Instead of inventing a whole new kind of line, we reinterpret that backward going electron as a positron moving forward in time. Same math, different storytelling. It's like saying, rather than think of this as the same guy walking backward, let's call it his mirror twin walking forward. But that's a choice of interpretation, not a necessity. The underlying structure doesn't force us to think in terms of many separate particles popping in and out of existence. It allows us to think in terms of a single continuous entity whose path is so tangled that, when we slice reality into moments of time, we see lots of separate appearances. Here's an analogy I like. Imagine a long piece of spaghetti dropped onto a table in a messy pile. Now take a knife and slice horizontally through the pile at a particular height. On the cut surface, you'll see many little circular cross sections of pasta. If you didn't know better, you'd say, wow, lots of little spaghetti pieces embedded in this slice. But really, it's just one long noodle looping around in 3 dimensions. The multiplicity you see depends on how you slice it. In our case, the slice is a moment of time. At any given instant, we see an enormous number of electrons spread throughout space. But that could just be the cross sections of one incredibly convoluted world line weaving back and forth through time and space. Now let's make it a bit more concrete with something we can actually measure. Electrons have charge, negative electric charge, and they repel each other. If you bring 2 electrons close together, they push apart. That's not philosophy, that's experiment. So if there were really only one electron, how could it repel itself? That sounds like arguing with yourself in a mirror and somehow shoving your own reflection across the room. But remember, in this picture, those 2 electrons repelling each other at the same time are just 2 different segments of the same world line that happen to intersect our present slice of time in 2 different places. From the space-time point of view, they're separated along the path, maybe by enormous stretches of time, even though to us they appear simultaneous. It's like watching a movie where the same actor plays multiple characters using clever editing. In one scene, he's arguing with himself across a table. From the audience's perspective, there are 2 people there. But in the full production process, it's one actor filmed at different times and stitched together. Nature's editing is better than Hollywood's. The stitching happens in 4-dimensional spacetime, and the interactions are governed by precise rules. When 2 segments of the electron's world line come close in spacetime, they interact through the electromagnetic field. The math doesn't require those segments to belong to different electrons in any deep sense. It only requires that charge and energy and momentum are conserved at each interaction point. So the idea of one electron doesn't break the rules of how charges push and pull. It just reassigns the bookkeeping. Instead of labeling lines electron Phi1, electron Phi2, and so on, you label them all as parts of one grand loopy trajectory. Now, you might be wondering, if this is even remotely plausible, why don't all physicists run around saying, good news, everybody, we found the one electron? Well, because physics isn't just about what you can imagine. It's about what the math demands and what experiments can distinguish. And here's where things get deliciously subtle. In quantum field theory, particles aren't really the primary objects. Fields are. There's an electron field that fills all of space. What we call an electron is a little excitation, a quantized ripple in that field, like a tiny vibration on the surface of a pond that otherwise looks flat. When you quantize the field, you naturally get the idea of many identical quanta, many electrons, because the field can be excited in many places at once. The formalism talks very comfortably about particle number 1 electron here, 2 there, a whole bunch over in that chunk of metal. But, and this is a big but, the particles that come out of the theory are still perfectly indistinguishable. The field doesn't attach identity tags. Swapping 2 electrons doesn't create a new physical state. It's the same state, sometimes with a minus sign in the math, which leads to all kinds of interesting consequences like the structure of the periodic table. But there's no hidden label underneath. So the one-electron universe idea is like taking that indistinguishability and pushing it to its most extreme philosophical conclusion. If there's no measurable difference between many identical electrons and one electron seen many times, then maybe the latter is the more economical story. It's a bit like asking whether ocean waves are separate objects or just patterns in one continuous body of water. You can count waves, measure their heights, watch them collide. But you wouldn't say there are a billion separate waters in the ocean. There's just water doing complicated things. In that sense, the electron field is the water and the electrons are the waves. The one electron idea goes even further and says maybe even the waves are all part of one grand, interconnected disturbance when viewed in full spacetime. Now let's play with a tiny thought experiment. Suppose you had a fantastically powerful microscope that could track an individual electron over time. You watch it zip around, scatter off atoms, get absorbed, re-emitted, all that jazz. In ordinary thinking, you'd say, I am following this particular electron. But because electrons are indistinguishable, the theory never promises that the electron you see later is the same one you saw earlier. The amplitude, the probability calculation, includes contributions from histories where the identity effectively swaps with other identical electrons. In quantum mechanics, when identical particles are involved, you don't just add probabilities, you add amplitudes for all the indistinguishable ways something could happen. That includes ways where the particles have exchanged roles. The interference between these possibilities is real and measurable. It changes the outcomes of experiments. So nature already behaves as if it doesn't care about individual identity at the particle level. What it cares about are the overall patterns allowed by the fields and symmetries. The one-electron picture is like saying maybe that's not just a calculational trick, maybe that's telling us something deep, that individuality, at the most fundamental level, is not part of the furniture of the universe. And if that makes you feel slightly uneasy, good, because we're very attached to individuality. You, me, this chair, that star. We like to think everything is a separate, self-contained thing. But down in the quantum basement, the walls between this one and that one get awfully thin. So now we've got this image, a single electron world line, twisting, looping, sometimes moving forward in time, sometimes backward, intersecting our present moment in countless places so that we perceive a vast population of electrons and positrons. The mathematics doesn't immediately forbid it. The indistinguishability of particles encourages the thought. The reinterpretation of positrons as backward, in time electrons gives it a mischievous wink of legitimacy. But the universe is a tough audience. It doesn't give standing ovations for pretty pictures alone. The real question is how far we can push this idea before it either breaks or reveals something profound about the structure of reality itself. Because once you start letting particles wander backward in time and merge into one grand thread, you're forced to rethink not just how many electrons there are, but what a happening even is, and whether the way we slice the universe into past, present, and future is more about us than about nature. Shall we tug on that thread and see what starts to unravel? All right, now we're really in the deep water, so let's keep our balance and not drown in our own metaphors. We've been entertaining this idea that what we call many electrons might be different appearances of one single entity tracing a wildly complicated path through spacetime. So now the question is, what does the actual machinery of physics say about such a picture? Where does it smile and nod, and where does it raise an eyebrow? Let's start with how we actually predict anything about electrons. We don't follow tiny billiard balls with little stopwatches. Instead, we calculate probabilities for different outcomes. If an electron goes from point A to point B, quantum mechanics doesn't say it takes one definite path. It says we must consider all possible paths connecting A and B, each with a certain phase, a kind of internal rhythm. And when you add them all together, you get the final probability amplitude. This is the famous sum over histories idea. The electron doesn't politely choose one trajectory like a well-trained dog. It explores every conceivable route, including ones that look completely ridiculous from a classical point of view, zigzags, loops, detours that would make a taxi driver blush. Now here's the twist. In relativistic quantum theory, some of those paths include segments where the electron moves backward in time, and the math doesn't collapse in horror. Instead, those segments contribute in a very specific, controlled way. When you reinterpret them, they look exactly like positrons moving forward in time. So the formalism already treats forward in time electrons and backward in time electrons as two sides of the same coin. That's not philosophical speculation. That's baked into the equations that predict scattering experiments to absurd precision. When two electrons interact, we draw diagrams with lines representing their histories. These lines can wiggle, emit photons, absorb photons, even briefly turn into loops that represent virtual processes. And crucially, when an electron-positron pair is created and later annihilated, you can redraw the diagram as a single line that bends around in time. From the standpoint of spacetime geometry, the difference between a pair created and destroyed and one particle changing direction in time is partly a matter of how you choose to label the diagram. The observable consequences come out the same. So the one-electron idea is like taking that flexibility seriously. Instead of saying, well, that's just a calculational trick, you say, maybe that's a hint that particle number is not fundamental at all. And in fact, modern quantum field theory agrees with that last part, though it doesn't insist on there being literally one electron. Particle number is not a sacred, fixed quantity. In many situations, especially when gravity or accelerating frames enter the picture, the very definition of how many particles are there depends on who's asking and how they're moving. What looks like empty space to one observer can look like a bath of particles to another. So already the idea that the universe contains a definite, countable set of electrons at all times is more slippery than your intuition would like. Now let's push on a potential crack in the one-electron story. In our universe, there are far more electrons than positrons. Ordinary matter is made of electrons and protons. Positrons show up in high-energy processes and radioactive decays, but they're rare and usually short-lived. If every positron is just the same electron going backward in time, you might expect a kind of balance, as many backward segments as forward ones. But what we see looks very asymmetric. This was noticed right away when the idea was first joked about. If there were literally one electron zigzagging through time, its world line would have to double back on itself an astronomical number of times to account for all the electrons we see now. And the mismatch between electrons and positrons would mean its path has a preferred direction overall. That's not impossible, but it starts to look less elegant. Still, elegance is a matter of taste. Nature isn't required to be elegant in ways that please us. What's more important is this: the equations of quantum field theory don't actually describe one continuous world line for all electrons. They describe a field with certain properties, and when you quantize it, you get operators that can create or destroy electron excitations. The formalism naturally talks about states with different numbers of particles. It's incredibly successful. It predicts the magnetic moment of the electron to more decimal places than you can count on your fingers and toes combined. So the mainstream view is electrons are excitations of a field, and there can be many of them. Full stop. But, and here's the philosophical wiggle room, the field itself is one entity spread throughout spacetime. The excitations don't have individual identity beyond their quantum numbers. In calculations, when we sum over histories, we already include processes where lines connect in ways that blur the distinction between this particle and that particle. So the one-electron universe can be seen as a poetic way of expressing a real feature of the theory, the deep indistinguishability and the primacy of the field over individual particles. Now let's turn the spotlight on time itself, because that's where this idea really starts messing with your head. We experience time as a flowing river. There's a present moment, a fixed past, and an open future. But in relativity, space-time is more like a four-dimensional block. All events, past, present, future, are laid out in this structure. Different observers slice this block into nows, in different ways depending on how they're moving. In that picture, a particle's world line is just a curve in this four-dimensional geometry. It doesn't move in time the way a car moves along a road. The whole curve just is. Our sense of motion is tied to how our consciousness crawls along our own world line. So if the electron's world line is some fantastically convoluted curve weaving back and forth in time, that entire curve could be part of the fixed space-time structure. What we call creation and annihilation. Events are just places where the curve changes direction relative to our chosen time coordinate. From this viewpoint, asking how many electrons are there right now is like asking how many times does this curve intersect this particular slice through space-time. Change the slice, change the answer. That's already true in relativity for more subtle reasons, but the one-electron picture makes it vivid. Multiplicity becomes a property of how we carve up space-time, not necessarily a fundamental count of independent things. Now, don't run away with the idea that physicists have secretly replaced all electrons with one cosmic spaghetti strand. We haven't. The standard framework works perfectly well without that interpretation, and it connects cleanly to the language of fields and particles that we use to design experiments and technologies. But what this idea does beautifully is expose how shaky our everyday intuitions are. We're used to a world made of little, separate objects with clear identities, marching forward in time like obedient soldiers. Quantum field theory and relativity together whisper, not so fast. Identity might be emergent. Particle number might be contextual. Time might be more like a dimension of space than a universal ticking clock. And the one-electron story is a playful, slightly outrageous way of packaging all those whispers into a single, unforgettable image. Instead of a universe filled with an astronomical number of tiny beads, imagine one thread, knotted and looped beyond comprehension, stitching together events across billions of years. Every electron interaction you've ever relied on, every chemical bond in your body, every electrical signal in your brain, would be different crossings of that same thread through the fabric of space-time. Which brings us to the part that always gives me a little chill in a good way. Because if individuality at the particle level is this blurry, if what looks like many can be reimagined as one extended structure, then the categories we use to carve up reality might be more about the limits of our perspective than about the ultimate nature of things. We see separate moments because we live inside time. We see separate particles because we observe local interactions. But the deeper description might be a single, interconnected tapestry where separation is a useful approximation, not a fundamental truth, and that doesn't make the world less real. It makes it more interesting. It means that beneath the solid, familiar surface of tables and trees and toes, there's a level where the universe is doing something far stranger and more unified than our everyday language can easily capture. The crazy part isn't that there might be only one electron. The crazy part is that the laws of physics even leave room for such a thought, and then go right on working, predicting experiments with outrageous accuracy, as if to say, believe whatever story helps you think, kid. The math's the same, and we're left in this delightful position building lasers, computers, and particle accelerators using a theory that quietly undermines our most basic intuitions about counting, identity, and the flow of time. Not bad for a little speck of charge with a bad habit of being everywhere at once.